we now understand what probability measure is. It is a set function with three basic properties: positivity, normalization, and most important of all, additivity. Before we move on and examine instances of probability measure in common situations and look at a wealth of applications, it would be well to start with this formal framework, this abstract framework, and see what we can extract directly by simple arguments. In other words, get the low-hanging fruit while we may. Okay? So let's start with a very, very simple question. What can we say about the probability of the event which is empty? Of course, our instinctive reaction is to say, well, the empty set should have zero probability. But you understand, in a formal theory, we can't simply include information from outside, as it were. Right? Think back to the axiomatic structure. What do we have? We have positivity. The sample space has got unit probability, and there's this idea of additivity. Nowhere in there is a mention of the empty set. So, of course, we could insert another axiom, the probability of the empty set being zero, for example. But it is not wise in mathematical investigations to overburden an axiomatic structure of assumptions. Theories are most intuitive and tend to have the greatest application and sway when the assumptions are spare, few in number, things which are easily checked. So it is preferable to get results like this, that the empty set has got zero probability, as a consequence of the axioms, rather than assume it a priori. So let's see what we can do with the axioms we have. Let's pick two events. Specifically, let A be the event comprised of the entire sample space. A is omega. And let B be the trivial event comprised of the empty set. Now, of course, these are very trite and banal in many ways, but there are certain obvious natural properties. What do we intersect these two? Well, anything intersected with the empty set is empty, and therefore omega intersection the empty set is empty. Or in our set theoretic language, the sets omega and the empty set are disjoint. Aha, this strikes a bell with the axiom of additivity, which dealt with disjoint sets. Well, to understand how to use it, we have to look at the union. But any set, when it's taken as a union with the entire sample space, will just give you the sample space. The sample space contains everything. Excellent. Now let's see what we can do with this. Begin with the axiom of normalization. The probability measure associated with the entire sample space is unit. But the entire sample space may be decomposed as the union of omega with the empty set, where these two objects, omega and the empty set, are disjoint. Additivity immediately tells us then that the probability of the union is the sum of the two probabilities. But on the right, we see the probability of the set omega, which by the normalization axiom must be unit. And notice, just by churning through the normalization and additivity axioms, we've got an identity. The bookend on the left is 1, the bookend on the right is 1 plus the probability of the empty set. Cancel 1 on both sides, and we are left perforce with the inevitable conclusion that the empty set must indeed have zero probability, as indeed it must.